I want to talk a little bit about Heisenberg's uncertainty principle. So Heisenberg is a German physicist, Werner Heisenberg, and he was around in the time of Niels Bohr and de Broglie and Albert Einstein and all these other kind of people that we've talked about in recent videos about quantum mechanics, if you've been watching any of those others. And the uncertainty principle is one of those things that that is just kind of tricky to get your head around because it just seems so physically improbable with the way that we understand kind of the macro level world. But when we get down to teeny tiny particle kind of level sizes, and again getting into quantum mechanics, then these features start to matter a little bit more. So the Heisenberg uncertainty principle says that the more certain we can be about the position of a particle in motion, so we have a teeny tiny particle, it's moving around, then the less certain we can be about its momentum. And so kind of the take-home message from this is that we cannot, with certainty, in a probability kind of sense, right, be 100% certain of both the position and the momentum of a moving particle. And again, this becomes more and more of a factor as I get smaller and smaller on a particle level. So let's think about this in terms of kind of a mathematical equation, or let's just try to picture what we're talking about here. So it says that we can't be certain about momentum and position. So momentum, which is symbolized by this kind of stylized P looking thing, is equal to the mass of the particle times the velocity. So we're looking at kilograms and meters per second here is your momentum. We can write that in there. And so momentum is large if the velocity is large, right? So if I'm moving really fast, then I'll have a large momentum. But also if I'm a very massive thing, even if I'm not moving very fast, then I'm still going to have a lot of momentum. Like a semi-truck, for example, right, is really massive. It doesn't have to be moving very quickly, not on the order of the speed of light, right, in order to cause some pretty serious damage. So the momentum there is related to both of these factors. And if we're relating this to position, then let's think about a particle. Particles in motion. Let's think about it being in motion along a single axis, because that kind of makes things a little bit easier in terms of our math. Once we start moving into multiple dimensions, of course, everything gets more challenging. So let's say that we're along the x-axis here. So the position along an x-axis is just going to be a coordinate, right? So I have a coordinate of where this particle is. It's pretty easy to determine the location of a particle, right? There it is. I found it, right? And then I can go, you know, here's my y coordinate, here's my x coordinate. Or if I'm just looking at this in one dimension, I can just say, where along my number line here am I, right? So that's the position of my particle. Now, if we factor both of these things in, then what Heisenberg says, Heisenberg's uncertainty principle says, is that the uncertainty in this momentum calculation and the uncertainty in this position calculation are going to be related to each other. And the more certain I am of one, the less certain I am about the other. And the way that we mathematically talk about this is by taking the uncertainty with respect to the position. So that's this here is not a change in x, this is uncertainty of position along the x-axis. And the relationship that he found is that when I multiply that by the change in my momentum, or again, not the change in my momentum, the uncertainty in momentum, sorry, I need to write it first instead of speaking. Write instead of speaking first, right? So we're used to thinking about deltas in terms of changes and looking at the way things change. And we are looking at changes here, but we're not talking about the change in terms of these measurements. This delta quantity is referring to how much uncertainty is. So plus or minus how much of each of these quantities am I unsure about them, right? So it really gives me a sense of precision of my measurements, right? Plus or minus how much of my x coordinate am I going to find this, within what range? And same with my momentum, within what range of momentum values am I going to find my particular particle falling into? And the relationship he found is that when you multiply these uncertainties together, it has to be greater than or equal to Planck's constant, Again, Planck's constant shows up quite a bit with quantum mechanical features over 4 pi. So this is a very small constant number, right? Pi is a constant, Planck's constant is a constant. Planck's constant, of course, is that 6.63 times 10 to the negative 34th joule seconds, and this is pi, so this is all a constant value. And these uncertainties then are going to have to be, when you multiply them together, greater than or equal to this tiny little number. And as I get smaller in terms of particle size, then the greater these uncertainties are. The more certain I am about one, the less certain I can be about the other. Now, because momentum relates mass and velocity, then I can kind of say, well, if my particle's mass doesn't change, which there's no reason that it should, right? Matter remains constant. We're talking about a lot of wackiness and uncertainty, but we're not uncertain about the mass of the particle changing, right? Then we can kind of unpack this uncertainty of my momentum here, and I could say that it's really going to be kind of, here's my uncertainty for my change in position times the uncertainty in my velocity in the x direction times my mass here. And all of that has to be greater than or equal to Planck's constant over 4 pi. And if I bring my mass over, if I divide both sides by my mass here, then I end up with this relationship where I have the uncertainty of the position times the uncertainty of the velocity, or the speed, is going to be greater than or equal to Planck's constant over 4 pi times the mass of my particle. And again, this being in the denominator like this really shows and highlights that as the mass gets large, then these uncertainties mean less, right? So as we increase the mass of our particle, then the greater amount of certainty we have about both of these things. And as the mass of our particle goes down, then vice versa. And from a physical standpoint, if I bowl a bowling ball down the alley, I can measure how fast it's going. I know its mass. I can tell where its position is along the lane, right? I'm not uncertain. I'm not like, where did the bowling ball go, right? Like it's there. I found it. So Heisenberg's uncertainty principle really just matters when we get down to teeny tiny particles, getting down into these quantum mechanical kind of features. Okay, so our mass is staying the same, so we're kind of lumping it in with the constant here. We can use this relationship then to solve problems that look something like this. So we can find out the uncertainty of the position of an electron, right? So now we're talking teeny tiny. Electrons have a mass of 9.11 times 10 to the negative 31 kilograms. It's moving at this particular velocity, so I know it's in motion, and because it's in motion, then I know that I can talk about its momentum, right? It has a velocity associated with it. And we have an uncertainty of the velocity of 0.05 times 10 to the 5th meters per second. So that uncertainty means that kind of within this range, plus or minus this, is my unknown factor, right? It's my squishiness in all of this. I can't be 100% certain, but I'm certain within this range, this value. So let's figure out what our uncertainty of position is. So by how much off am I going to be if I'm looking for the change in position? So let's take our equation that we were just looking at. My uncertainty of position is this delta x value. And if I rearrange and put my delta v there at the bottom, then I could say that it has to be greater than or equal to Planck's constant over 4 pi times my mass, right? That's what I had before, and now I divided both sides by my change in velocity. Again, not change in velocity, uncertainty in velocity. Oh, that's a hard thing to break. Okay, so let's plug in our values then. We know Planck's constant is 6.63 times 10 to the negative 34th. Units on that are in joule seconds. 4 and pi are both just values, right? And then our mass is given 9.11 times 10 to the negative 31 kilograms. And then my uncertainty and my velocity is given here. 10 to the 5th meters per second. Now, if we're doing a little unit analysis, just kind of right off the bat to make sure that the units that we've put together with our setup here make sense, recall that a joule is equal to a kilogram meter squared per second squared. And that times a second then is going to give me a kilogram meter squared per second on the top. My kilograms will then divide out. My meters per second will divide those guys, and I'll be left with an answer in meters. So my uncertainty in my position is going to be greater than or equal to, and then when I kind of plug and chug this into my scientific calculator, I get 4.63 times 10 to the negative 8th meters. So I'm going to have a greater or equal uncertainty to this amount, this length. Right? So I have at least this amount of uncertainty, if not more, depending on kind of other factors that are at play there. So that's the uncertainty principle. It gives us a way to calculate by how much we are uncertain about either the position or the momentum. And we can either talk about it in terms of the uncertainty of the momentum, like we originally set up, or we can kind of unpack it and talk about it with uncertainty of the velocity if we're given that information. Now you may look at this and say, well, why did you even give me the velocity then? Well, part of that is that it's always good to have more information, and information that we don't need than not enough information. But this just shows that I'm moving, right? It's just giving you a sense of speed. You know that I'm moving really quickly. It's a teeny tiny particle. So we know that it has a pretty healthy momentum because of the speed, but it's going to be very still smallish because of the mass, right? And so this just gives us some information about context, but not something that I used in my calculation itself, because the calculation itself was just looking for the uncertainty in the velocity, not in the velocity itself. So that's something to keep an eye on as you're doing these types of calculations in whatever applications you're doing them in. Okay, so that's a little bit about Werner Heisenberg and the uncertainty principle. You've probably heard of Heisenberg maybe from Breaking Bad, if you're a chemistry student and you're interested in such things. You know, of course, Heisenberg as his nom de guerre. And so a lot of pop culture references to Heisenberg these days. But the uncertainty principle really boils down to this idea that quantum mechanical things are funky. As we get smaller, then quantum mechanical features and the wave nature of these particles becomes more prevalent and more important, and that causes us to not be able to measure things to the degree of certainty that we want. And then for that reason, we have to rely on probabilities. How likely, how certain. We have to cage all of our values in kind of these uncertain terms. And that's going to have impacts on the way that we understand what the atom looks like when we talk about things like atomic orbitals. So keep an eye out for that, and I'll talk to you again soon.